Okay, good evening, everybody. My name is Leong. I'm sure the chairman has already introduced me. So I'm going to present this topic on stability of trees in the urban environment. I first acknowledge my collaborator, Dr. Darrell Lee from Huge Research, who belongs to National Parks Board in Singapore. Okay, the scope of my presentation will be divided into 5 sections as shown on this slide. I first want to give you a background. When you come to Singapore, you land in the Singapore airport, and when you leave the airport, you'll see that the roads are lined with trees. So National Parks Board actually plays a big role in this greenery in Singapore that we have. Okay, the greenery policy or the greening policy in Singapore started in 11 May 1967 by our first Prime Minister, Lee Kuan Yew. His vision was to transform Singapore into a garden city so that we achieve a city with abundant large greenery and a green environment for the people. As we move on, about 20 years later, there was another bigger vision. We want to transform Singapore into a city in a garden. Okay, and we are now actually at the end. We have sort of moved on. So in April 2020, from Singapore being a city, there's this new vision of city in nature. There's currently a 1 million trees movement being launched by NParks. So that what we are planning to do is to plant 1 million trees across Singapore over the next 10 years. So trees in Singapore to more than 8 million. Okay, in 10 years' time. Okay, there are about 2 million trees planted along roadsides in parks and state land. This is actually under the jurisdiction of the National Parks Board. So the 10 most common trees are listed on this slide. I'm not going to go into the names because it may not be familiar to you. Okay, as this comes with a price of greening because occasionally we get trees that fail, and this is one common mode of tree failure. The entire tree actually overturn and fall. Okay, and this is another one that falls in a housing estate. So these trees, when it fall down because of the self-weight of the tree, it can cause a lot of damage. If it falls on infrastructure, or worse still, it falls on some people. So it can cause fatality. Okay, now I move on to the methodology of this research that we have in collaboration with National Parks Board Singapore. Basically, if you want to study the problem of stability of trees, we can use 2 approaches. Okay, the first approach is just to survey a tree that has been damaged after storm. That's what you have seen in the previous 2 slides. So we go on site to survey the trees, take measurements of whatever we could. Or the second approach is to conduct tree pooling tests. Sorry? Sorry? Am I okay?
Yeah, you are online. You are up and running. You are all right.
Okay. Okay. Okay, so if we approach to survey tree damage of the storm, wait for the storm to occur and then get reports of tree failure, quickly move on to the site to actually survey. So sometimes this is an impossible task. Like for example, this particular storm that happens on 2nd of March 2011 is a freak storm. There's about 10,000 trees from 150 species were damaged in a 40-hectare zone. So this area is very large. It's as large as 80 football fields. So basically, when you have such a storm, you take a lot of manpower just to go and map the trees. But being a city state, the main concern is to make sure that all these trees are cleared as soon as possible. Okay, so as not to obstruct traffic and leaving a trail of debris, which could be risky for road users. Okay, there are also storms like this that uprooted a certain number of trees. For example, this one in 18 September 2016, So there are a number of trees being uprooted in so-called a park area. Okay, and this about 200 trees that fell after a heavy storm in 2018. Okay, so sometimes you have trees falling into more prominent area. This is Scott's Road near the tourist belt, Orchard Road. So this can create a lot of bad publicity as well. Okay, and this fell on a playground. So luckily no children were injured. This actually occurred after heavy rain. So all this this particular method of conducting research, the advantage is of course low cost because we just wait for the event to happen and then go down to site and do a survey. But basically, we do not exactly know what is the forces that cause the tree failure. So the trees that fail may not be healthy. So only seeing the trees that are unhealthy being uprooted. So this approach is actually more an opportunistic. We have to wait for the storm to occur, which is not planned. So we do not know when it will occur or whether it will occur at all. Okay, and it's a passive approach. All we can do is to sit and wait for these events to occur. Okay, for us, we have chosen to adopt the tree pulling test to assess tree stability. Okay, our main aim is to see whether we can make sense of the data that we collect from tree pulling tests so that we can reduce the risk of tree uprooting. Yeah, tree pulling test is not new. This is done very often overseas. They have a tree that they want to find what is the resistance, and they attach a cable, and you have instruments on the tree as well as a load cell on the winching cable. Okay, so basically they can determine how much force is it need to pull over the tree. Okay, so sometimes these trees are not pulled until destruction. So the advantages of this tree pulling test is that we can control the test conditions. We can select the tree and plant the measurement points. We can obtain very accurate quantitative measurements. Okay, the only disadvantage is that this is a static pulling test. It does apply the same force as the wind. So we have to somehow translate the readings to an equivalent wind force on the tree to evaluate of this tree uprooting under certain wind force. Okay, for this project, we have selected 6 street trees to study. These are the trees that's listed here. Again, I think I'm not going to go through this may not be familiar to us being more geotechnical engineers. Okay, now I'm going to the tree pulling test that we have conducted. Okay, so you have the same sort of setup with some modifications. So we have our tree for safety reasons. Some of this tree crown or what we call canopy here could be quite large, so that we can move our instruments to be quite close. We use a tow truck to provide the winching force rather than using another tree as the anchor point. Okay, and then we actually have a mechanical advantage by using a pulley system of 2 to apply the force on the tree. So basically, we remove the crown of the tree, and we know that the soil strength is going to change at different degree of saturation. So most of these tree failures occurs during the storm or after the heavy rain. So basically, we saturate the tree root zone as much as possible. Hopefully, it's almost fully saturated before we start the test. So we put up instruments onto the trees. So the instruments are very comprehensive. We have to measure the bending strain, we have elastometers, LVDTs. To measure the tilt, we have accelerometer, tilt meter, as well as an inflometer made by. So on top of that, we actually have sort of points put on the These are being recorded by the camera system. Okay, that is at a short distance away, about 10 to 50. Okay, so these markers allow us to track the movement of the tree as the tree pulling is in progress. So we had a comparison between the different type of measurement instruments. For example, for the inclination of the tree, we compare our tilt meter reading, our accelerometer reading, this Picus inclinometer, as well as from the camera, okay, using those points that we see. Down here is shortened as camera vision, but you can call it a PIV, particle image velocity. Okay, they operate on the same principle. So basically, you can see that the instruments have different limits. So with the camera, we can actually track displacement. For the load measurement, we have it on the cable, okay, or the cable that we attach through the pulley. So we have a load cell that we record to take that measurement. So this is just a video of the tree pulling test that we have conducted. All right, this just a sampling of the recording that we trees that were being pulled over. So after the tree pulling test, we actually recorded because we need to know what is the extent of this root plate cavity. So the root plate cavity from this recording, we actually can get from 3D models like this. So we can know what is the extent of this cavity. So this will provide our additional information when we do the analysis. So we will take a look at what type of analysis and how we apply the test results. Okay, so we have the pulling force, we can actually work out what is the critical moment at the base of the tree. So this is a compilation of all the test results. So what we found is that there is some sort of relationship. You can see that it is not so easy because the root system is quite variable. It's different from tree to tree, even for the same tree species. Okay, so the different tree species are represented using the different color markers here. Okay, so we have find that this relationship between the critical overturning moment with this TPH squared, which is being used heavily by the people in the arborists who studies trees. This DVH is actually the diameter of the trunk at about 1.3 meters height, okay, from the ground level. H is the height of the tree. So this roughly gives you the so-called the weight of the tree. So from here, we can see that there's some sort of relationship that we can use. Okay, as mentioned, from tree pulling tests like this, for this information, the only thing that is missing is that we need to relate this back to the wind force to understand how this will become unstable during a storm. Okay, so roughly from this relationship, we know that critical overturning moment increases as the tree become larger and larger. Okay, to relate it to the wind force, we can use this method. What is this area, this frontal area, subjected by a wind force. The wind force acting on the trunk. Okay, wind force is related using this equation where you have 0.5 times the density of the air. A is the area on which the wind force acts. CD is the drag coefficient. V is the wind velocity to the power of squared. So the destabilizing moment for this tree is basically this wind force acting on the crown multiplied by this height H1, this wind force WF2 acting on the trunk here multiplied by H2. And when the tree tilts over, there is an additional contribution from the self-weight of the tree multiplied by this distance D. Okay, so this is the destabilizing moment. Okay, so what we see from this graph here, this critical overturning moment is what we call so this is the observer resisting moment, this destabilizing moment. So using these two information, we can then relate to the velocity of the wind causing this instability. So if you know what is your wind velocity, you can use this to assess whether we have enough resisting moment to overcome this wind loading. So we also did a further in-depth study into the tree from this data that we obtained using finite element. So we are able to actually simulate the response very well, actually. Okay. So what you see is actually the three component actually working. This is showing the stresses in the trunk. This is shown in the root plate, and this in the soil. Okay, so this allows us to take a closer look at the mechanism that is causing this failure to take place. Okay, the magnitude of stresses are different. That's why you are seeing three different animations. The trunk being sort of properties of timber, it can withstand very high stresses. The root plate actually took one order lower stresses, and the soil actually is another order lower. Okay, so in order to be able to visualize the stresses, we have to use three separate, divide the animation in three separate parts. Okay, so this allows us to take a look what is actually happening when we conduct this tree pulling test. Okay, so finally, I will just do a conclusion. Tree pulling tests provide useful data to understand the stability of trees. The critical overturning moment that we obtain is dependent on a number of factors such as tree species, the root plate dimensions, and the soil properties. The critical overturning moment with the dBH squared H relationship provide a way to assess a tree stability under wind load. So we can use this to actually assess whether a tree is in danger of failing under certain storm condition. Okay, so with this is the end of my presentation.